Welcome to Podcast Learn and Fun. Let's start today's journey of learning. We often talk about how things change, like the weather, the stock market, or even how we learn new things. But did you ever wonder how we can actually predict or model these changes in a reliable way?
It's a fascinating question, and it turns out there's a whole branch of mathematics dedicated to understanding and predicting change, particularly in complex systems. We called these mathematical tools partial differential equations, or PDEs for short. They may sound intimidating.
Yeah, they do.
But they're really just equations that involve rates of change with respect to multiple variables.
Okay, so it's like taking calculus to the next level. Instead of just dealing with change in one variable, we're now looking at how things change in relation to multiple factors all at once.
That's a great way to put it. Think about trying to predict the temperature in a room. The temperature might change over time, of course, but it also varies depending on where you are in the room. Closer to the heater or further away. So we have at least two variables influencing the temperature, time and location.
I'm starting to see how this gets complicated quickly.
Yeah.
We're not just dealing with a simple line graph anymore.
Right.
We're talking about changes happening in multiple dimensions.
Exactly. And that's where PDEs come in.
Oh.
They provide a framework for describing how these multidimensional changes occur and how they relate to each other.
This is reminding me of something I vaguely remember from calculus, something called the heat equation. Does that ring a bell?
Absolutely. The heat equation is a classic example of a PDE.
Okay.
It describes how heat flows through a material over time. Imagine you're heating a metal rod.
Okay.
The heat equation can tell us how the temperature at any point on that rod changes.
Right.
Both with time and with its position along the rod.
Okay. That image makes it a bit easier to grasp.
Yeah.
But if these PDEs are dealing with so many variables at once, how do we even begin to solve them? They sound like incredibly complex puzzles.
You're right. They can be quite challenging. But thankfully, mathematicians have developed some clever techniques to tackle these puzzles.
Okay.
One particularly powerful technique is called separation of variables.
Separation of variables. I'm intrigued. Tell me more.
Imagine you're trying to untangle a complicated knot.
Okay.
The best way to do it is to separate the strands one by one, right? Separation of variables works in a similar way.
Okay.
We essentially try to break down the complex PDE into smaller, simpler equations that we can solve individually.
So instead of trying to solve for everything at once, we're separating the problem into manageable chunks.
Precisely. It's like dividing a big project into smaller tasks.
Right.
In the case of the heat equation, we might try to separate the part that describes how the temperature changes over time from the part that describes how it changes with position along the rod.
I'm starting to get the gist of it, but it still sounds pretty abstract. Can you walk me through how this actually works?
Let's stick with our heated rod example. With separation of variables, we assume we can express the solution to this heat equation as the product of separate functions, each dealing with only one of the variables. We'd have one function describing how the temperature changes with time, another describing how it changes with position.
So it's like we're creating a formula where one part handles the time aspect and the other part handles the position aspect, and then we multiply them together to get the complete picture.
You got it. And the amazing thing is that when we substitute the separated form back into the original heat equation, something magical happens.
What's that?
The equation simplifies, and we end up with separate equations for each of those individual functions.
Oh, wow.
These simpler equations are often much easier to solve.
So we're essentially transforming a really complex equation into a set of smaller, more manageable equations that we actually know how to deal with.
Exactly. And these simpler equations are usually something called ordinary differential equations, or ODEs, which are the bread and butter of calculus.
Okay, so we're breaking down the complexity and bringing it back to familiar territory. I like where this is going.
It's like taking a complex machine and disassembling it into its individual parts.
Right.
By understanding how each part works, we gain a deeper understanding of the machine as a whole.
This is fascinating. It's like we're taking a peek behind the curtain and seeing how mathematicians can tame these seemingly unruly equations.
Yeah.
But there's one thing that's still bugging me.
Okay.
We've talked about separating variables and solving for these simpler functions.
Right.
But how do we ensure that our solution actually reflects the specific scenario we're trying to model?
Yeah.
Like, how do we make sure it accurately describes the heat distribution in that metal rod we were talking about?
That's a great question, and it brings us to the crucial role of what we call boundary conditions and initial conditions.
Okay.
Think of these as the specific rules that govern our system.
Okay, so let's unpack that a bit. What exactly do we mean by boundary conditions and initial conditions?
Think about our heated rod again. The initial condition tells us the starting temperature at every point along the rod.
Okay.
It's like a snapshot of the temperature distribution at the very beginning of our experiment.
Got it.
Boundary conditions, on the other hand, define what's happening at the ends of the rod.
Okay.
Perhaps we're keeping the ends at a fixed temperature, or maybe they're insulated.
So the initial condition is like the starting point of our journey, and the boundary conditions are like the walls or fences that guide the path of the heat flow.
That's a perfect analogy. The initial condition sets the stage, and the boundary conditions establish the rules of the game.
I see. So these conditions help us tailor our general solution to the specific scenario we're dealing with.
Right.
But how do we actually incorporate them into our mathematical framework?
That's where things get really interesting, and it involves a concept that might sound a bit intimidating at first: Fourier series.
Fourier series. That rings a bell, but I can't quite place it. Can you refresh my memory?
Think of it this way. Any complex temperature pattern along our rod, even something seemingly random, can be broken down into a sum of much simpler wave patterns.
Oh.
These waves, called sine waves, have different frequencies and amplitudes, and by combining them in just the right way, we can recreate any temperature distribution we want.
It's like taking a complex sound wave and breaking it down into its individual frequencies. Like how a music equalizer lets you adjust the volume of different frequencies to shape the overall sound.
That's a brilliant analogy. The Fourier series is like a mathematical equalizer for our temperature distribution.
I see.
It helps us find the right volume or coefficient for each of those sine waves.
Okay.
So that they add up perfectly to match our initial temperature profile.
Okay, so we're essentially using these simple sine waves as building blocks to construct a complex temperature pattern. It's like a mathematical Lego set for heat.
Exactly. And the way we determine those volume settings or coefficients is through a process called integration. It's a way of ensuring that our solution not only satisfies the heat equation itself, but also fits perfectly with the initial conditions we've set.
Wow, this is all starting to click now. It's amazing how a seemingly complex problem can be approached in such a systematic and elegant way.
Yeah.
But I'm curious, can we apply these same ideas to even more complex situations? What if we're not just dealing with a one-dimensional rod, but something like heat spreading across a two-dimensional surface like a frying pan?
That's a fantastic question, and you're right on the mark.
Okay.
The beauty of this separation of variables technique is that it can be extended to handle PDEs in higher dimensions.
So instead of just separating for time and position along a line, we could separate for time and position along the x-axis and position along the a-axis. Like we're adding more dimensions to our mathematical Lego set.
Precisely. The core principle remains the same, just with more variables to juggle.
Right.
We'd still be breaking down a complex problem into simpler solvable pieces.
I'm starting to see how powerful this mathematical framework can be. But before we get too carried away with all the technical details, I want to take a step back and make sure our listeners are still with us.
Okay.
Can you help me summarize what we've learned so far?
Absolutely. We started by talking about how change is all around us.
Right.
And how we can use mathematical tools to understand and predict these changes.
Mm-hmm.
We introduced the concept of PDEs.
Yeah.
These powerful equations that can handle changes happening in multiple dimensions at once.
We dove into a specific example, the heat equation, which describes how heat flows through a material.
Right.
And we explore this clever technique called separation of variables.
Yes.
Where we essentially break down a complex PDE into smaller, simpler equations that we can solve individually.
We also talked about the importance of boundary conditions and initial conditions.
Yeah.
These are like the rules of the game that help us tailor our solution to the specific scenario we're trying to model.
And then you introduced us to the amazing world of Fourier series, where we can break down any complex pattern, like a temperature distribution, into a sum of simple sine waves.
Exactly.
It's like having a mathematical equalizer for heat.
By combining these sine waves with just the right coefficients, which we find through integration, we can perfectly recreate the initial temperature distribution and ensure our solution accurately reflects the real-world scenario.
This is all incredibly fascinating. But I have to admit, it's a lot to wrap my head around.
Yeah.
It makes me wonder, why should the average person care about PDEs and all this mathematical wizardry? It seems pretty abstract and far removed from everyday life.
That's a fair point.
Yeah.
But what's fascinating is that PDEs, though seemingly abstract, are constantly at work behind the scenes shaping the world around us.
Really? Can you give me some examples?
Think about something as simple as listening to music on your phone.
Okay.
The algorithms that compress that music into digital files and the speakers that convert those digital signals back into sound waves, they all rely on PDEs to accurately model and manipulate those sound waves.
Wow, I never thought about it that way. So we're literally surrounded by PDEs, even if we don't realize it.
Exactly. They're embedded in the technology we use every day.
Huh.
Consider the weather forecast you check each morning.
Okay.
Meteorologists use complex PDEs to model the movement of air masses, predict temperature changes, and forecast those rain showers that might make you grab an umbrella.
So PDEs are helping us predict the unpredictable. That's pretty impressive.
And it goes beyond weather forecasting.
Really?
Think about the design of airplanes and cars.
Right.
Engineers use PDEs to analyze airflow and optimize shapes for better fuel efficiency and performance.
So PDEs are making our cars sleeker and our planes more aerodynamic. It's starting to feel like they're involved in almost everything.
They really are.
Wow.
The development of new materials, understanding the flow of traffic, predicting stock market fluctuations, all of these fields rely heavily on PDEs to model complex dynamic systems.
Okay. I'm convinced.
Good.
PDEs are way more important than I ever imagined. But all this talk about solving them and separating variables is making me feel a little overwhelmed. It makes me wonder, are there ever situations where this separation of variables trick doesn't work? What if the equations are just too complex to untangle?
That's a great question, and it highlights an important point.
Okay.
While separation of variables is a powerful technique, it's not a magic bullet.
Right.
There are certainly PDEs out there that are so complex that separating variables becomes extremely difficult or even impossible.
So what happens then? Do mathematicians just throw up their hands and give up?
Of course not.
Okay.
They're a persistent bunch.
Yep.
When separation of variables fails, they turn to other more advanced techniques.
Like what?
Some of these involve using numerical methods and computer simulations to approximate solutions. Others involve developing entirely new mathematical frameworks to tackle these challenging equations.
It sounds like the world of PDEs is full of mysteries and challenges, constantly pushing the boundaries of mathematical knowledge.
It absolutely is, and that's what makes it so exciting. Each new discovery opens up new avenues for exploration, leading to innovations that can have a profound impact on our world.
Speaking of further exploration, before we wrap things up, I want to leave our listeners with something to ponder.
I'm all ears.
We've talked about how separation of variables can help us break down complex systems into smaller, more manageable parts.
Right.
But it makes me wonder, are there limits to how far we can break things down? Is there a point where things become so fundamentally intertwined that even the most brilliant mathematicians can't separate them?
That's a deep question, and it gets to the heart of some of the biggest mysteries in science and mathematics.
Yeah.
How much can we truly understand about the universe? Are there ultimate limits to our knowledge?
It's both humbling and exciting to think about.
It is.
It reminds us that even with all our scientific advancements, there's still so much we don't know.
Exactly. And those unanswered questions are often the most intriguing. They drive us to explore, to experiment, to keep pushing the boundaries of what we thought was possible.
On that note of endless curiosity, I think it's time to wrap up our deep dive for today.
Okay.
It's been an incredible journey exploring the world of PDEs and the remarkable ways they shape our understanding of the universe.
It's been a truly mind-expanding journey. We've gone from thinking about everyday changes to exploring the elegant mathematics that underpins those changes.
I feel like I've gained a whole new appreciation for the hidden world of PDEs. They're not just abstract equations on a blackboard. They're the language that describes how our universe works, from the smallest sound waves to the largest weather patterns.
And what's truly remarkable is that even with all the complexity we've uncovered, there's still so much more to discover. The field of PDEs is constantly evolving, with mathematicians developing new techniques and pushing the boundaries of what we thought was possible.
It's inspiring to think about. Who knows what incredible breakthroughs await us in the future? Maybe one of our listeners will be inspired to delve deeper into this fascinating field and make their own contributions to solving the mysteries of the universe.
That would be fantastic. After all, the journey of learning is never truly finished. There's always another layer to uncover, another question to ask, another puzzle to solve.
And speaking of those unanswered questions, I think we've left our listeners with plenty to ponder. We've touched on the limits of our knowledge, the interconnectedness of seemingly separate phenomena, and the endless potential for discovery.
It's those very questions that keep us curious, keep us exploring, and ultimately keep us moving forward.
So to all our listeners out there, the next time you encounter something complex and seemingly incomprehensible, remember that even the most intricate phenomena can often be broken down into simpler parts. And who knows, you might just find yourself unraveling a mystery that no one has ever solved before.
It's been an absolute pleasure exploring the world of PDEs with you and our listeners today.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.